Okay, this is the last section from Green's theorem. It's alternative forms for Green's theorem. So it's still 15.4. So these two alternative forms will kind of allow us to get through the end of the book. We still have to do some sidetracking with 15.5 and 15.6. But 15.7 and 15.8 kind of evolved from these alternative forms. Okay? So we're going to connect we'll do some connections of these integrals to the operators that we established earlier in chapter 15. So first one we want to look at is foreshadowing Stokes' theorem. And let me remind you of Green's theorem. What the heck does Green's theorem say? It's basically if you have this line integral around this simple curve, and we write it in differential form, so m dx plus m dy, we can rewrite that as a double integral over this the region that is bounded by this curve. Okay? And then this double integral will be the double integral of the partial derivative of n with respect to x minus the partial derivative of m with respect to y, okay, dA. Okay. From the section before, if you've forgotten, the other way, the more familiar way, I think, of writing that integral is the line integral of the vector field f dot dr. Okay, and there were like three versions of the way we would write it, but just to remind you that we also saw this. So this is Green's theorem. Okay, Green's theorem. Kind of extract that so I can let it make an appearance here every now and again in my notes. Okay, so there it is. Green's theorem. Okay. So the first thing we're going to do is foreshadow Stokes' theorem. And in order to do that, we're going to note the connection between the curl operator and Green's theorem. Okay, so let's just remind ourselves what is the curl of f. If we have a vector field given by m, n, and p, so a vector field f, m, and p, the curl of that vector field, you would kind of figure it out by doing a determinant type function, mechanics, whatever. So you would have the I, J, K, and then you'd have these partials, which really symbolizes the action you're doing on the vector field. Okay. So I would, cover that junk up and kind of do a determinate action there. So it would be py minus nz for the first component. So the partial of p with respect to y minus the partial of n with respect to z. And then negative partial of p with respect to x minus the partial of m with respect to z. And then the partial of n with respect to x minus the partial of m with respect to y. Okay, and so why is that important? It's because this third component looks an awful lot like the insides of this part of Green's theorem, right? If you rewrite that, n sub x is the partial derivative of n with respect to x, m sub y is the partial of m with respect to y. And so that thing there, that part is this part. Okay, so what? Well, I could now put our Green's theorem into this curl kind of notation. So instead of writing the double integral of this thing, I dA, I can now rewrite it as the double integral of the curl of f, kind of. I have to dot it with the k vector in order just to extract this one component. right? So what the heck was k? K is equal to 0, 0, 1. So when you dot k with the curl, this times this will be 0, this times this will be 0, and then this times this will be 1 times this, which is just this, which is what we want inside our integral. Okay, okay, so you'll see that rewrite, kind of. Okay, once we get to Stokes' theorem, we need to do a little bit more with, I think, surface integrals in order to pull it off, but that's kind of it. Okay, we already have it, kind of. All right. The other guy then is a foreshadowing of the divergence theorem. Okay. And in this case, we need the divergence of f. So we may remind ourselves, if we've forgotten, it's basically the sum of the partial derivatives of the components. Okay, so they notated it like this symbol dotted with f, and then that would be equal to the partial of m with respect to x plus the partial of n with respect to y, assuming f is just mn as opposed to mnp. All right, now this thing here, if you go back to Green's theorem again, looks an awful lot like the guts of Green's theorem. And in fact, that's what we're going to do in this case. We just kind of aren't there quite just yet. And in particular, what we'll be working with is the integral of a dot product of the force field with the unit normal vector integrated with respect to arc length. Okay. Okay, so there's two kinds of dot products we look at. It's basically the dot product with the unit tangent vector and the dot product with the unit normal vector. So if you think about our curves here, so here's our closed curve. On that curve, you'll have a unit tangent vector, but you also have a unit normal vector, which will either point inside or outside. In our work, we want the one that points to the outside. And this dot product will kind of tell you the alignment between the force field vector at any given point and either the unit tangent vector or the normal vector. Okay? If you're worried about the unit tangent vector, you're asking how much alignment is there between the force field and the unit tangent vector. And I think that will be kind of like the swirliness of it. And then if you're looking at the dot product between the force vector and and we're going to get the physical interpretation when we get the 15.7, 15.8, so don't take my word for it yet. Okay. Then the dot product with the normal vector is kind of considering the flow through the boundary of the region. You can even think of it now in terms of masks, right? With our coronavirus, what's the what's the sum of all of the breath vectors going through your mask? That you would want to know how perpendicular your breathing is, the air coming in and out of your mouth is with the mask, right? And that will kind of tell you how much flow there is through the mask. Okay, so definite applications all over the place here. But anyways, we're trying to connect this to the Green's theorem, right? So in order to pull this off, I'll note that I'll be given some vector value function for the curve C, so I can rewrite that as x of s, comma y of s. So we in terms of arc length. Then the unit tangent vector is just the derivative of this. So if you remember, the unit tangent vector was the derivative of r of t divided by the magnitude of the derivative of r of t, but the magnitude of the derivative of r of s is just equal to 1. So we could just replace the unit tangent vector with the derivative of r. And this will just be the derivative of the components. Okay. And then for the unit normal vector, we learned when it was in the plane, there was this clever little trick we could pull, which was just swapping the components of the unit tangent vector and negating one of them. And because we want the outward pointing vector as opposed to the inward pointing, we're going to make the first one negative and the second one positive. Okay, so we're rewriting this using this information. And so what do we have? So it's the integral of m comma n dotted with this thing. Let's rewrite it as the derivative of y with respect to s, and that has to be negative, comma the derivative of x with respect to s times ds. And if we kind of abuse the notation, we can think of this as this times this times this, and the ds's will cancel. So we'll end up with the integral of m comma n dotted with negative dy comma dx. And then we can dot product those, and what you get is kind of a differential form for the line integral. Okay, so this will be m negative m dy plus n dx, which then looks an awful lot like the right-hand side of Green's theorem, but not exactly, right? Because the y is in the wrong place and the x and one's negative. But you could still apply Green's theorem. Okay? It doesn't matter that these are out of order. M and n are just functions of x and y, so why would it matter, right? So we can then apply Green's theorem to this and rewrite it as a double integral of the partial of m with respect to x. Instead of going minus, we'll go plus because of that negative, plus the partial of n with respect to y over whatever region we're worried about, dA. And then lastly, we can replace the guts with the divergence operator, because the guts right now, the integrand, is exactly this guy right here. Okay? So I could replace the integrand here with the divergence operation. So this would be just the divergence of f dA over r. And basically what you have is kind of like a lower dimensional version of, well, it's not even a lower dimensional, I think. But we'll see when we get there. Let me not get ahead of myself. Okay, but those are going to lead into Stokes' theorem and then Green's theorem, divergence theorem. So you may want to kind of backtrack and look at these videos again once we get to explaining those two theorems in 15.7 and 15.8, which will be the last sections in the book. We kind of already have all of it. We just have to go back now and worry about surface, I believe it's surface integrals. Okay, all righty then, we'll see you later.